So let's look at power models and see how data appears in a power model. In a power model, what we'll find is that as the independent variable changes by a constant factor, the dependent variable will change also by a constant factor, and it won't be the same common factor. So let's look at this set of data. I have some data here that my independent variable goes from 1 to 8, and I have dependent variable going from 14 up to over 300. Now if I graph the data, I would definitely find a curved pattern, so many people would think initially that it might be some type of an exponential curve. However, it's not. I've tested for exponential. I took, as my independent variable increased by a constant amount of 1, I checked to find what the quotient was if I divided the 39.6 by 14. I got that to be about 2.8. Then when I take the 72.75 and divided it by the 39.6, I did not get 2.8. And I found that when I pairwise did these quotients that they were very different from 2.8. So I know that the exponential model doesn't follow. So I thought, well, let's try the power model. I have a limited number of data points here. I only see up through 8. So I'm going to look at what happens as I double my independent variable. So 1 times 2 being 2. I know that that ratio is about 2.8. So I look at my data and look for another place where I can see the independent variable doubling, 2 to 4. And when I take the 112 divided by the 39.6, I find that that ratio is also about 2.8. I have another pair of points. 3 times 2 is 6. And if I compare this and this, and take the 205.76 and divide it by the 72.75, I find once again that I get that common ratio of about 2.8. I had one more set I could check, although I was pretty sure that this looks like it's going to have this pattern of power, but 4 times 2 is 8, so I took 316.78 and divided it by 112, and I got 2.8. So that's what characteristic you'll see for a power model, that as you have a independent variable changing by a constant factor of 2, that my dependent variable is changing by a constant factor of 2.8-ish. Now, we can find what the missing exponent is for our power model actually a couple different ways. And our power model is going to take on the form of y equals a times x2, a constant power. I'll write it over here. Y equals a times x2a constant power, n. That's a constant, as is the a value. And so we have to figure out what that value is. One real quick way is whatever this factor change is for the independent variable, if we take the factor change to the nth power, that will be what this resulting factor change was when we had this quotient. And so I could very nicely solve this equation with taking the log of each side, or use the definition of a log, to determine what that n constant value is, and that would be the power of my power function. Another way to do it is, once we can identify that that power pattern has occurred in our data, is we can do the similar thing that with n exponential, is we write down what the general form is for the power function, and then use a couple of our points. We have two unknowns, an n and an a, that are constants, and we just need to set up a little system of equations so that we can determine what those values are. I did that. I used the point 1 and 14. I used the point 2 and the 39.6. And then I'd have to solve that little system of equation. Nicely enough for this one, because of being given the point 1, I actually know what the a constant is. And then I could go back through and solve my little system, as I've shown here. I won't go through all the steps, but I'll display them for you to go back and look at on your own. But I used this a value, and then went through and solved for n. So this would be the technique if you are just solving a system of equations, knowing that it's a power function, writing a system with two of the points being used to determine the missing constant n and a. However, remember, it's easiest if you remember the characteristic that whatever the factor change was that you saw here, that factor change raised to the n power, which is the constant you're looking for, is what this resulting factor will be over here from taking your common ratios. So there's our power function.